Let's start lecture 22, and the course is corrosion protection methods. The broad topic what we have been discussing for last few lectures is basically the materials aspect for corrosion protection. And in the last lecture what we started is material selection, and a material selection under general corrosion or uniform corrosion. And we have seen that if we fix a kind of allowable corrosion limit or the failure limit, like let us say 0.25 millimeter per year for 10 carbon steel, and a lower corrosion limit is set for costly materials like stainless steel, it is 0.1 millimeter per year, and there we can design the component very nicely, because we know that the corrosion pattern is general. So, that means all throughout the cross section the dissolution would be more or less uniform. But things become very difficult to evaluate as well as monitor when it is localized attack. So, we will talk about the material selection under localized attack form. So, the course is corrosion protection methods, lecture 22, materials aspects for corrosion protection, and we talk about material selection under localized attack. Okay. Now, we know that there are two major localized attack patterns. So, what are those two patterns? One is pitting, another one is crevice, and when we have those, the selection of material becomes very conservative, as well as monitoring also becomes difficult. We will see why. Now, there are other localized forms also, like intergranular, de-alloying. We will concentrate our discussion on de-zincification. That means dissolution of zinc preferentially from brass. Then we have erosion corrosion, and apart from that we can have stress effect. It can be stress corrosion cracking, stress corrosion crack, corrosion fatigue, and you have hydrogen embrittlement, hydrogen induced cracking, we can say this. Okay. So, these are stress effect. Also, this is a localized pattern. Okay. So, we will also try to find out materials for these kind of forms of corrosion attack. Now, when we talk about pitting and crevice, these are very common, and let us first concentrate on those two localized forms. See, if we start with pitting, of course, pitting is very difficult to evaluate. Or monitor. And material selection becomes very conservative. Now, couple of things which are associated with pitting. One is this actually is associated with metallurgy challenge, as well as surface character. So, metallurgy challenge means if we have inhomogeneity on the surface composition, or if we have two phase regions, or if we have precipitation kind of situation, then it becomes more pit prone. And what we mean by surface character? Surface character means if we have a surface inhomogeneity from the point of morphology or the pattern of the surface. If the surface is rough, then the pit formation becomes easy. If surface is smooth, pit formation becomes difficult. Those kind of characters I am talking about. So, it poses two challenges, one is material challenge as well as surface character. These are two factors which are important. And another character is every material, every metals and alloys, if we talk about only metal or alloy, can experience pitting. Only thing is, it is decided by several other factors, like mainly if we consider the environment. If something is not forming pit, for example, if we consider stainless steel, it will not experience pit in case of fresh water and if it is moving, but it can form pit if there are chlorides and stagnant. So, that means stainless steel is also experiencing pit. For example, mild steel or plain carbon steel, they can also experience pit in NaCl solution. Okay. So, even titanium alloy can also experience pit, depending on whether the condition is conducive for the pit formation. But generally, some of the alloy systems like nickel based, copper based, titanium based, where we experience excellent passivity and regenerative passivity. Like, what do we mean by regenerative? Let us say passivity is lost, the material can actually reform the passive layer with no time in that particular solution. That time we can experience very good pitting resistance. And at the same time, those materials who are forming passive layer, if it is spontaneous passivity, I am not talking about active passive behavior, spontaneous passivity. So, then that material can actually provide excellent pitting resistance, as well as provided another condition should be satisfied, which is the surface film should be strong enough, as well as it should give a very high resistance to the charge flow. So, that means every metal and alloy can experience pitting. That means we have to decide after doing good amount of experimentation which material to be selected for a particular environment. Okay. So, now coming to a situation like, let us say, let us have a discussion on plain carbon steel. So, plain carbon steel generally it experiences general or uniform attack, but if this plain carbon steel is exposed to soil condition, soil exposure, and if the soil contains following like localized concentration cell or in the form of aerated one, like one place we have higher oxygen, one place we have low oxygen. So, high oxygen part can act as cathode, low oxygen part will act as anode, and accordingly the anode part can experience serious pitting. Then we can have a bacterial effect. Then also we can have stray current. Stray current is if you have a pipeline like this and this is below the earth crust or in the soil, and if on top of it or close to that, let us say, so we have another pipeline system So, if this is under cathodic protection, let us say we have used a cathodic protection or let us say impressed current cathodic protection, which is this part is minus, this part is positive. So, if we have this is my auxiliary anode, and this is the pipeline which is to be protected. Okay. So, if this is the cathodic protection we are using for pipeline, one set of pipeline, the another set of pipeline which is just below that protection system. So, if this pipeline is not there, the pipeline below that pipe system 2, if that is not there, then in absence of this pipe system 2, we can have nice flow of current like this, and then the circuit is complete. So, you have current flow like this and electron flow like this. So, pipeline is protected. But once we have another pipe system, and if that soil can carry electron or the current, so sorry, soil will carry the current in the form of ion movement. So, then the current path could be like this, and then it will leave here. Okay. So, this way this actually happens due to stray effect. So, now this current path becomes the green color path, it is moved like this. Okay. So, then we know wherever current leaves, so this place current leaves. So, that portion is the corrosion prone portion or region, and here we can have serious pitting. So, here we can have pitting. So, that means the stray current, this is basically a typical stray current effect. Okay. So, one way to protect is we can actually, what we can do, we can make this pipe system part of the pipe system 2, and let us say if the pipe system 1, this is pipe system 1. So, 1 and 2 can be taken a part of the common protection system. So, what can be done? We just can connect this one with this, and then we can connect this thing to, sorry. So, what can be done? If we connect this pipe system 1 and pipe system 2, then actually all the way, all current will move to this as well as to this. So, the entire pipe system 1 as well as 2 will be part of the cathode, because we are connecting the pipe system 2 and pipe system 1 to this negative terminal. What we can do like this, we can connect this, we can connect this. So, all the way the pipe system 1 and 2 are connected. So, that way we can protect both the pipe system together by using cathodic protection or impressed current cathodic protection, and we can avoid stray current effect. So, there also wherever the current leaves the pipe system 2, we can have serious beating effect. So, to avoid this, in those kind of situations, to avoid this, we have to use some sort of the remedy. We can use non-metallic coating, so that non-metallic coating will exert lot of resistance to the current flow, or we can use combined cathodic protection. In case of stray current or cathodic protection, cathodic protection could be sacrificial anode or impressed current cathodic protection. So, these two methods can be useful. So, similarly, if we try to see mill scale effect, so plain carbon steel, if it is hot rolled steel, then there would be a thin layer of oxide that remains on the steel. So, that is basically nothing but the mill scale, and that mill scale, if it remains on plain carbon steel and if there is a break in that mill scale. So, let us say this is my steel surface and we have a mill scale. So, let us say this is my cross section and this is the mill scale. And if we have H2 and O2, these two are present, moisture, and if there is a break in the mill scale, let us say, and also if it is within the soil also, that can, this can also lead to pitting, but if a small portion is broken. So, small portion is exposed. So, this part is exposed. So, once this part is exposed, so that part can act as anode. Since mill scale is, so this is iron, mill scale is basically cathodic in nature. Okay. So, now we have a large cathode. So, this is large cathode and this particular portion is small anode. Okay. So, then this region will have a serious attack and that can be in the form of pit. Okay. Very localized pit forming, and because of this galvanic effect which is created due to a small break in the mill scale. So, that is where the advisable remedy could be, we can use shot blasting to remove mill scale completely. Okay. So, that way we can avoid such kind of localized corrosion point due to the cathodic effect of the mill scale and anodic effect of that small exposed area due to the break in the mill scale. Now, question is, if we try to see the materials for aggressive medium, under aggressive medium like chloride containing solution, then material selection becomes further tricky. We have to go for peat resistance, peating resistant alloy system. In case of stainless steel, if we consider 304 stainless steel, it is austenitic and typical composition is 18% chromium, 8% nickel and carbon of the level of 0.08% carbon. But once we add little bit of molybdenum into it, around 2 to 4%, then the variant that comes out is basically 316 stainless steel. Okay. And if we reduce carbon again, so carbon content drops to 0.02 to 0.03%, these are all weight percent. So, all those changes from here to this, it actually improves the pitting resistance. In fact, molybdenum, addition of molybdenum improves the pitting resistance greatly. We can also use 317 variation. So, these two suitable for chloride exposure, and it is basically aqueous medium if we talk about. Now, we can also think of 317 stainless steel, SS317, which contains little more some other alloying elements, and chromium and nickel contents are little less, are little more than 304. So, here chromium could be of the order of 19%, nickel could be order of 13%, manganese 2%, around 2%, silicon 1%, and of course, carbon here it does not change much, this is 0.08%, but molybdenum is of the order of 3.5%. So, this is another steel variance which can offer very good pitting resistance. So, in those kind of situations we can use this 316 or 317, and once we reduce the carbon content, then the variant's name becomes SS316L. So, we call it 316L. So, L means low carbon, and as we decrease the carbon content, pitting resistance improves because we do not have much of inhomogeneity due to the carbide formation. So, what happens if you have a microstructure like this? So, let us say chromium carbide locally, even in the grain, instead of grain boundary, if it forms within the grain body, so those local portion can be pit forming portion. Okay. So, if we reduce carbon, the chromium carbide formation possibility minimizes to a great extent. So, then pitting resistance of course would increase. Now, in case of much more aggressive medium, so then we can think of higher addition of chromium and molybdenum. So, these two actually provide good amount of resistance to pitting. So, some materials which can be thought of like nickel based superalloy, sorry, not nickel based alloys. So, we can think of nickel based alloy like Hastelloy. So, the typical composition nickel 51 to 63.5%, cobalt is 0 to 2.5%, chromium 14.5 to 16.5%, molybdenum around 15 to 17%. So, the extremely high level of molybdenum, so that actually gives a excellent pitting resistance, and we have little bit of iron, tungsten and little bit of manganese 0 to 1%. So, this is a typical composition of Hastelloy. Okay. We can also use Inconel. So, there we have little less molybdenum, but the chromium content goes up. So, there nickel is of the level of 65%, chromium of the level of 22%, molybdenum 9%, and there could be presence of niobium about 4%. So, you could see that the cost wise these two are extremely costly, but they can offer extremely high pitting resistance. So, this is excellent pit resistant alloy. Okay. That is what in pump systems can be made of nickel based alloys in chloride medium. Now, titanium based alloys also offer excellent corrosion resistant under pitting condition, aqueous chloride medium, or in the presence of oxidizers. For example, pit resistant in aqueous chloride medium plus strong oxidizer. So, what are those strong oxidizers? Like ferric chloride, because it has +3 plus electron equal to +2, E naught with respect to hydrogen electrode standard hydrogen electrode, its value is 0.77 volt, which is extremely strong oxidizer. Or we can also have copper chloride, where copper plus E, copper plus 2 electron, it can take copper. So, E naught with reference to standard hydrogen electrode is 0.34 volt. So, that means they are strong oxidizers. Even in presence of those oxidizer, these titanium based alloys can provide good corrosion resist, good pitting resistance. So, these are some of the alloy systems, and now you could see that wherever the pitting ability is very high, and we have also seen in terms of corrosiveness as well as corrosion resistant plot, more the aggressive medium, restrictive would be the higher would be the restrictiveness to select materials, and of course, the cost part would also come in. As we see that in comparison to general corrosion prevention, for pitting corrosion prevention, because it is a localized pattern, we need to go for stainless steel, which is also high alloy steel, nickel based alloys which contains lot of molybdenum, Hastelloy, Inconel, or titanium based alloys, which is also a very costly alloy system. Now, for pitting kind of situation, some of the things must be taken care of, some of the aspects. So, what are the aspects to be taken care of? That means those kind of aspects must not be experienced during operation if there is a possibility of pit. So, combination, mainly combination of metal or alloy system and environment. If we talk about this, so couple of things we should be careful, like aluminum alloy system, true is for pure aluminum also, and if that alloy system is operating with some fluid, which contains heavy metals like copper, lead, even iron, Hg, which is mercury. So, then that case aluminum alloy can experience serious pitting. Okay, this is care for pitting. Then we should not use plain carbon steel or low alloy steel. In water with dissolved oxygen, okay, or soil with sulfate reducing bacteria. And third thing is austenitic stainless steel. Austenitic stainless steel, mainly the weldments of austenitic stainless steel. In a stagnant natural water. Mainly the underground water. So, these cases the material can experience serious pitting. So, this is about the material selection with reference to the pitting corrosion or a severe localized form of corrosion. So, we will discuss material selection in other localized forms like crevice, de-alloying, intergranular corrosion, as well as erosion corrosion and stress effect in our next lecture. Thank you.